In this video, you will be introduced to drag, which is a great way to get your feet wet in fluids. So, why does this video matter to you? Well, you'll be constructing robots that will be traveling through seawater. An understanding of what causes drag, as well as being able to estimate the drag forces acting on your robot, will be useful in determining how much thrust your robot will need to travel through water. A knowledge of drag force can also influence the design of your robot. This video also matters because when you become practicing engineers, you could be working on projects that involve a vehicle or object moving through a fluid. Minimizing drag is essential for numerous applications, such as fuel-efficient cars that reduce greenhouse gas emissions. To get started in fluids, think of the last time you stuck your hand out of the window of a moving car. For those of you who haven't done this, I commend you on your ability to resist this urge. For those of you who have done this, think about how your hand felt when you oriented it in the manner shown in this picture. Let's superimpose a coordinate axis. In this case, the positive y direction is pointing up, the positive x direction is pointing to the right, and the z positive direction is pointing into the page. Let's assume your vehicle was moving forward, so the incoming air has a velocity v and is moving in the positive x direction. A hand has a number of features that make the calculation of forces rather complicated, and the goal of this video is to introduce you to drag. Therefore, let's simplify our calculations by approximating a hand as a flat plate. This looks a little funny, but it's going to make learning the concepts in this video a lot more straightforward. So, here is our flat plate. Let's look at it from the side. Here is a two-dimensional view of the flat plate. The flat plate experiences two stresses as it interacts with the surrounding fluid. First, it experiences surface shear stresses due to viscous effects. These act in the x direction. The flat plate also experiences normal stresses due to pressure effects. These act in the y direction. When the flat plate is oriented in this manner, the flow of air above the flat plate is the same as the flow of air below the flat plate. The normal stresses on each side of the plate counteract each other, and therefore the plate is not pushed up or down. A slight force in the x direction occurs due to surface shear stresses. If you orient your hand in this manner when you stick it out of a moving car, you will see that your hand will not go up or down, but you'll feel a slight force on your skin, which is in the direction of the flow. So now, imagine your hand rotated 90 degrees so that the palm of your hand is oriented towards the incoming air. For those of you that have done this in a moving car, try to remember how it felt. You may have had to tense your arm muscles to keep your hand from smacking into the car window. What is this force? Again, you can approximate a hand as a flat plate. The coordinate axis is shown here. Let's take a look at the two-dimensional view of this flat plate in this orientation. Here's a view of the plate that is normal to the flow. Surface shear stresses act in the directions shown here. In this orientation, the pressure forces on the front of the plate are now higher than the pressure forces on the other side of the plate. In this orientation, the force is entirely due to the pressure difference between the front and back of your hand. You don't feel your hand move up or down because pressure forces act parallel to the upstream flow. Furthermore, shear stresses are symmetrical about the center of the plate. However, the plate will move in the positive x direction because the pressure forces on the front of the plate exceed the pressure forces on the other side of the plate. In this orientation, there is a net force in the direction of the upstream velocity. This net force is denoted by this yellow arrow. This net force indicated by the yellow arrow is drag, which we define as a net force that is parallel to the upstream flow due to pressure and shear forces on the surface of an object. Now, let's take a look at a three-dimensional view of the flat plate. If the flat plate has a thickness L, height h, and width w, we can calculate the drag force with the following equation. This is the equation for drag force. Rho is the density of the fluid in units of kilograms per cubic meter. If you are calculating the drag of a car, then you would use the density of air in this equation. If you are calculating the drag on an underwater robot, you would use the density of seawater at the depth that your robot will be traveling. V is your upstream velocity in units of meters per second. A is the reference area in units of square meters. Now, knowing which reference area to use in fluids problems is very important. I repeat, knowing which reference area to use in fluids problems is very important. We'll be going over which area to use in a future video, when we combine the concepts of lift and drag to discuss wings, propellers, and turbine blades. In this case, the flat plate oriented in this manner is a blunt body. When considering blunt bodies, the reference area is the area seen by an observer looking at the object from a direction parallel to the flow. In this case, the reference area is width times height h. Now, C sub d is the drag coefficient. We will be spending a lot of time discussing the drag coefficient in future videos. For now, know that C sub d is a very important coefficient that considers the effects of both shear forces and pressure forces. Now, let's take a look at how the drag equation could be used in the case of a person riding a bike. Think back to a time that you rode a bike. Maybe you were riding a bike to class. You were most likely in an upright position. In this case, rho is the density of air on the day that you were riding the bike, and v is the velocity of your bike. If you were not in a rush, you were probably traveling at 4.47 meters per second, or 10 miles per hour. In an upright position, a typical reference area for a person is 0.51 square meters, and the drag coefficient in this configuration is 1.1. Let's now take a look at the case where the rider of the bike is in the position shown. In this position, the rider has a smaller reference area of 0.36 square meters. Furthermore, the coefficient of drag in this position drops to 0.9. If you've ever watched a bike race, such as the Tour de France or in the Olympics, you'll see a biker leading a pack of other bikers, but you'll see the other bikers following closely behind the leader. This is called drafting. Due to fluid effects, the coefficient of drag of the biker that is following the leader is actually lower than the coefficient of drag of the leader, which means that the drag force of the biker in the rear is lower than the drag force on the biker up front. This results in the biker in the rear expending less energy to move forward. The fluid effects that cause the drop in coefficient of drag are beyond the scope of these introductory videos, but you will learn about this in your future engineering courses on fluids. Now, drag force can really be reduced by putting a fairing on top of the bicycle. Although this increases the reference area of the rider, it drastically reduces the drag coefficient. Bikes with such fairings can be seen in competitions, such as the ASME Human-Powered Vehicle Challenge. Drag is very important in the design of fuel-efficient cars. In this picture, you can see how the coefficient of drag has gone down due to vehicle design over the last 100 years. The design, with the theoretical minimum coefficient of drag of 0.15, is shown here. Think about this shape the next time you see an energy-efficient car like the Toyota Prius or the Honda Insight. Drag is very important in the design of underwater vehicles as well. In the graph on the right, you can see the effect of the length to diameter ratio on the coefficient of drag of a submersible. This is why the cigar shape, with a high length to diameter ratio, is a common one for underwater vehicles. Now let's apply what we've learned through this quiz. Imagine that you are on a school bus that is traveling at 27.78 meters per second. For some strange reason, a person on the bus decides to pop the square emergency hatch open while the bus is moving. The square hatch has sides that are 0.5 meters long and a thickness that is 0.05 meters. Calculate the drag force on the bus hatch. You will be needing the following information, and your choices are shown on the left. Pause the video now, work out the problem, and pick one of the possible solutions. Unpause the video to see the solution to this quiz. The correct answer is B. We know the velocity and the density of air. The area of the bus hatch is 0.5 meters times 0.5 meters, which is 0.25 square meters. The coefficient of drag is 1.9 based on the ratio of thickness and side length. Plugging these into the drag equation results in a drag force of 225 newtons. In this video, you were introduced to surface and shear stresses that act on objects that move through a fluid. You learned that these stresses give rise to a drag force, which is a net force that is parallel to the upstream flow. You also learned about the drag coefficient, which considers both the effects of shear and pressure forces. The drag equation is shown here.